Hello everyone, welcome to this lecture. In this lecture, we are going to study Legendre polynomials and Rodrigue's formula. And in the previous lecture, we have found the solution of Legendre equation. This was the Legendre equation: 1 minus x square y double dash minus 2xy dash plus alpha alpha plus 1 equals to 0. And we have already found the solution of this equation. And the solution was this: y equals to c naught, a series, plus c1, another series, right? This was the solution, and this solution we have found in the previous lecture. Okay, so I can write this solution as c naught y1 plus c1 y2, where y1 is this series in the bracket, this infinite series, and y2 is this series in the bracket. Okay, so and both of these series are convergent, and these series are converges for x between -1 and +1. This can be verified easily using the series convergence test. Okay, now since y1 contains even powers of x, so here you can see that y1 has even powers of x and y2 has odd powers of x. Therefore, y1 divided by y2 is not a constant. It will never be a constant, right? So therefore, from here we can deduce that y1 cannot be a constant multiple of y2, right? So y1 cannot be a constant multiple of y2. So this implies that y1 and y2 both are linearly independent. So we have y1 and y2, two linearly independent, right, functions, series, right? So here you can see that c naught y1 plus c1 y2. If you take c naught as 1 and c1 as 0, c naught and c1 both are arbitrary constants, right? Remember that c naught and c1 both are arbitrary constants. So if I take c naught as 1 and c1 as 0, so we'll get only y equals to y1. So that means y1 is a solution of Legendre equation. Similarly, if we take c naught as 0 and c1 as 1, so we'll get y equals to y2. So that means y2 is also a solution of Legendre equation. So we have two linearly, and both y1 and y2 are linearly independent solutions. So that means this Legendre equation, y1 and y2 are two linearly independent solutions of this Legendre equation, right? Okay, so now two linearly independent solution of Legendre equations are y1 and y2. So y1 is this and y2 is this, right? So both of these series, right, series solutions. So two linearly independent series solutions we have, y1 and y2 of the Legendre equation. Now let's move to the next slide. So if you put alpha equals to 0, in y1, then y1 will be 1. You can check that. So this is our y1, and if you put alpha equals to 0, then this term will become 0 and rest of the terms will also become 0. So we'll get y1 equals to 1 only. And if you put alpha equals to, similarly if you put alpha equals to 2, so we will get y1 as 1 minus 3x square. And if you put alpha equals to 4, and then y1 will be this, and y1 will be 1 minus 10x square plus 35 by 3 x raised to power 4, right? So you can check that for these are even integers, 0, 2, 4 and 6 and so on, right? So so these are for even integers. y1 is what? y1 is a polynomial, right? y1 is a polynomial. And for these integers, for even integers, if you check that, if you see y2 is what? So if you put 0 here, you will get an infinite series. If you put 2 here, you'll get an infinite series. So for even integers, y2 is an infinite series, and y1 is a polynomial of degree alpha, right? So whatever be the alpha, if alpha is a positive, even positive integer, then y1 is a polynomial of degree alpha, and y2 is an infinite series, right? So now look for alpha equals to 1. If you see for alpha equals to 1, we will get y2 as x, right? You can check that, you can verify that. And for alpha equals to 3, we'll get y2 equals to x minus 5 by 3 x cube. And for alpha equals to 5, we'll get y2 equals to x minus 14 by 3 x cube plus 21 by 5 x5. So these are odd integers, right? So for odd integers, y2 is a polynomial, right? And y1, you can check that y1 is an infinite series, right? So when alpha is an even integer, then y1 is a polynomial and y2 is an infinite series. And when alpha is an odd integer, then y2 is a polynomial and y1 is an infinite series, right? So these polynomials, right? These polynomials we are getting for alpha equals to 0, 1, 2, 3, 4, 5, and so on. So these polynomials multiplied by a suitable constant are called Legendre polynomials, right? So, and the Legendre polynomials of degree n is denoted by Pnx. So we will denote it by Pnx. And the suitable constant would be such that this satisfies Pn1 equals to 1. So that means if we put 1 in place of x, then Pnx would be 1, right? Okay, so now we have, so P naught x, that means we are denoting Legendre polynomials by Pnx. So what is P naught x? What is P naught x? So put in place of n, so P naught x would be the Legendre polynomial of degree 0. That means this polynomial, right? This is the Legendre polynomial of degree 0. So this is P naught x is y1 multiplied by some suitable constant a. We will find that constant, right, using this condition. So we will use this condition. So this is y1 is 1 because y1 is 1 here. So this is equals to a times 1 and this is a, and when we use this condition, we have p naught 1 as 1. So this implies that p naught 1 equals to a. P naught 1 is a, since, right? So p naught 1 is a, so that means, and p naught 1 is what? 1. So we'll put p naught 1 as 1. So a equals to 1. So we'll get a equals to 1, right? So that means our Legendre polynomial of degree 0 is 1. Similarly, we can find Legendre polynomial of degree 1, which is here, y2 equals to x. So we'll find the suitable constant here. So p1x is a times y1x, and this must be y2. So this must be, so a times y2x, right, for alpha equals to 1. So this is this is equals to a times, because y2x is x, so this is p1 now we'll put x equals to 1 in this. So p11 is a, so that, and p11 is 1, so a must be 1. So here we'll get a equals to 1, therefore p1x equals to x, right? So similarly we'll get p2x as minus 1 by 2, 1 minus 3x square. You can easily verify this, right? So, and p3x will get 1 by 2, 5x cube minus 3x square, right? Similarly, you can find other polynomials also. Hello everyone. In the previous lecture, we have studied Legendre polynomials, and we have found some Legendre polynomials of degree 0, 1, 2, 3, and 4. And it's very difficult to find Legendre polynomials of a higher degree, suppose of degree 10. So there is a formula which generates the Legendre polynomials of any degree, and the formula is called Rodrigue's formula. And the Rodrigue's formula is this. This is Rodrigue's formula. This is Pnx equals to 1 by n factorial 2 raised to power n dn nth derivative. This means nth derivative of x square minus 1 raised to power n. Okay, so we will prove this formula. So let's see the proof. So let u is x square minus 1 raised to power n. This is equation number 1. And now we will differentiate this with respect to x. So I'm denoting the first derivative of u by u1. So u1 would be, So differentiate this with respect to x, we will get n x square minus 1 raised to power n minus 1 into 2x, right? This is easy, right? You can easily find the derivative of this, right? Now, so u1, I can write this u1 equals to 2nx. So I have taken this term and this term together, 2nx, and x square raised to power x square minus 1 raised to power n minus 1. I can write this as x square minus 1 raised to power n divided by x square minus 1, right? Okay, so now I can write this as like this. So I have make some arrangements. So I have multiplied the whole equation by x square minus 1. So we will get x square minus 1 u1, and here on the right hand side we'll get 2nx x square minus 1 raised to power n, right? So x square minus 1 raised to power n is u from equation 1. So we will replace x square minus 1 raised to power n by u in the next term or so. So this is equals to, now I can write this x square minus 1 as minus of 1 minus x square u1 plus 2nx x square minus 1 raised to power n, and this is equals to, this implies that 1 minus x square u1. So I have taken this this term to the right hand side. So I'll get 1 minus x square u1 plus 2nx and x square minus 1 raised to power n. I have written this u, right, from equation 1. So this is equals to 0, and this is, let's say this is equation number 2. Now where u1 is du by dx, right? I have already told this that the u1 is the first derivative of u, right? Now now we will differentiate this equation number 2 n plus 1 times, right? So we will differentiate this n plus 1 times, and we will use here the Leibniz theorem. So Leibniz theorem states that if we have two functions u and v, and then their nth derivative, so here d is denoting the nth derivative of dn is denoting nth derivative of the product of those two functions u and v. U and v both are functions of x, let's say. So the dn uv denotes the nth derivative of this product. So this is equals to nc0 dnu dn first function times v plus nc1, and in the next term dn minus 1. So this reduced to 1. So now we have n minus 1th derivative of u and first derivative of u, right? You will see that the sum of the powers here, so here is n, and this is just a simple v, so I can denote it by d0. That means the 0th derivative, which is the function itself. So the sum of these two would be n, right? So here n plus 0 is n minus 1, and here it is 1, so n minus 1 plus 1, which is n. So in all the terms it will be n. So nc1 dn minus 1 u plus into dv, and in the next term we will have nc2 dn minus 2 u and d square v. Again the sum of the derivatives, the derivative power, this power, right, n minus 2 plus 2 is 0, right, sorry, n, right, and so on. So it will goes up to ncn u dn v, right? So we will apply this formula to differentiate equation second n plus 1 times, right? Okay, so this is our equation number 2, 1 minus x square u1 plus 2nx u equals to 0, and we will differentiate this n plus 1 times, right? So differentiating this with respect to x n plus 1 times, we will get, so I can write this as dn plus 1, this, right? So I'm taking 1 minus x square as v and u1 as u in this term, right? So, and in this term we will take u as u and x as v, right? Okay, so this is, so I'm differentiating this n plus 1 times with respect to n plus 1 times using Leibniz theorem, right? So we will have n plus 1 c naught because we are differentiating n plus 1 times, right? So we'll have n plus 1 here. So n plus 1 c naught dn plus 1 u1, and the second function, that is v, would be as it is, right? This is the first term, plus we will have n plus 1 c1 now, and here it will be n, right? So it will be reduced by 1. So it is dn u1 and d 1 minus x square, and in the next term we will have n plus 1 c2 dn minus 1 u1 d square 1 minus x square. Now what would be the next term? In the next term we will have d cube 1 minus x square, so it would be 0, and so the rest of the terms would be 0, right? So the differentiation and of this function, this term 1 minus x square u1 n plus 1 times is this only, right? Now we will differentiate this term with respect to n plus 1 with respect to x n plus 1 times. So we will get 2n, so I can take 2n out, right? And then dn plus 1 u x, here also of course here it will be n plus 1 c naught, which is 1, right? And the next term would be n plus 1 c1 dn u dx, and in the next term we will have d square x, which would be 0, so we don't need to write it, and rest of the terms would also be 0. So the n plus 1th derivative of this is this only, and so this is equals to 0, right? Now let's come to the next. Now we will make some arrangements. So n plus 1 c0 is 1, and dn plus 1 u1 I can write it as un plus 2, and u1 1 minus x, okay, this, so 1 minus x square is 1 minus x square only, plus, now let's see what is this. So this term is n plus 1, and n plus 1 c1 is n plus 1, and dn u1 is, I can write this as un plus 1, right? This is u1 is the first derivative, and dn is the nth derivative of u1, so that means we will have n plus 1th derivative of u, right? So, and the derivative of 1 minus x square is minus 2x plus n plus 1 c2. N plus 1 c2 is what? So n plus 1 c2 is n plus 1 n by 2 factorial, and this is dn minus 1 u1 is un, and now differentiate this twice, so you'll get minus 2, right? And in the next term we will have plus 2n, so I have multiplied this, so 2n x, and this is un, un plus 1, and this is, next term is 2n, this 2n, and here we will have n plus 1 c1 is n plus 1, and this is un, and dx is 1, right? So this is equals to 0, right? Now this is un plus 2 1 minus x square is as it is, and here it is minus 2nx, so I have multiplied here, so we'll get minus 2nx un plus 1, and now I will multiply this term in this, so we'll get minus 2x un plus 1, and this term is now 2 will be cancelled out, and we'll get minus here, so minus n plus 1 un plus 2n x un plus 1 as it is, and this term is also as it is, right? This is equals to 0. Now in the next term I can write this as 1 minus x square un plus 2, and now you can see that 2nx un plus 1 and minus 2nx un plus 1, and this is plus 2nx n plus un plus 1, so this will be cancelled out, right? So we are left with minus 2x un plus 1, and here see that n plus 1 un, and we have 2n plus 1 un, so after adding these two terms we'll get n plus 1 un equals to 0, right? Now what is our Legendre equation? So this is equals to, I can write this as 1 minus x square un double dash minus 2x un dash plus n plus 1 un equals to 0, right? So now let's say this is equation star. Now what is our Legendre equation? So our Legendre equation is 1 minus x square y double dash minus 2x y dash plus n plus 1 y equals to 0. Now compare these two equations, star and this Legendre equation. You can see that in place of y here it is only un, right? So that means un is satisfying Legendre equation, right? un is satisfying Legendre equation. That means un is a solution of Legendre equation, right? un is a solution of Legendre equation. So now since Pnx is finite series solution of Legendre equation, Pnx is the Legendre polynomial, right? And Legendre polynomial is a solution of Legendre equation, right? So therefore we will have Pnx as c times this un, right? Because Pnx is a finite series solution of Legendre equation and un is also a solution of Legendre equation. So that means this is equals to c times dn and dxn x square minus 1 raised to power n. And now for Legendre polynomial, we know that Pn1 is 1, right? So this is the condition of Legendre polynomial. Pn1 is 1. Therefore Pn1 is c times dn un. The un is this, and x square minus 1 raised to power n. I have written this as x minus 1, this, right? X minus 1 raised to power n, x plus 1 raised to power n. X square minus 1 can be written as x minus 1 into x plus 1. That's why this is this, right? Okay, so now c times, so now we will differentiate this n plus nth time using Leibniz theorem. So we will apply Leibniz theorem here. This is u and this is v, right? So we'll get nc0, nth derivative of x minus 1 raised to power n, and v is this, plus in the next term we will have nc1, and we will have a power dn minus 1 x minus 1 raised to power n. So we'll have a power of x minus 1 here in the second term and in the subsequent terms also, right? So we will have terms containing x minus 1 and its higher powers. So Pn1, this would be x at x equals to 1, right? So at x equals to 1. So this is also at x equals to 1. So we'll get Pn1 equals to this, and Pn1 is then this c n factorial. So nth derivative of x minus 1 raised to power n is n factorial, and this term is as it is, plus terms containing x minus 1 and higher and its higher powers, right, at x equals to 1. Now in the next term we will have n factorial c n factorial, and this is, we have just put the value x equals to 1 in the bracket. So we'll get 2 raised to power n, and the rest of the terms would be 0 because it contains x minus 1, right? So rest of the terms would be 0. So we are left with Pn1 equals to c times 2 raised to power n factorial, and this implies that because Pn1 is 1, so 1 equals to 2 raised to power n factorial c, and from here c is 1 by 2 raised to power n factorial, right? So we found the value of c. Therefore Pnx is 1 by 2 raised to power n factorial dn dxn x square minus 1 raised to power n. So we have just put the value of c. Pnx is this. This is Rodrigue's formula.